Okay, so we're going to take a look in section 10.4 at polar coordinates. So most of you have said you've seen them before, but just a real quick recap to remind you of how that works. The polar coordinate system is a system using coordinates based on the distance from the origin, referred to as r, and the angle measure from the positive x-axis, and we call that theta. And I've put some space in here for us so that we can draw a picture as a reference. Our ordered pairs, are listed as r theta. And if I have a particular point somewhere, we'll put it right here, then we would measure the distance. I'll use a different color. Back to the origin. So this is the r value. It's this length right here. And we measure the angle measure right here. And our point is determined by those two pieces. Now, that means it's not unique. That is to say, there's not one ordered pair for that point like there is in rectangular coordinates. In rectangular coordinates, there's an x and a y point that is that exact point, and there's nothing you can do about it, right? I mean, there's no other option. But you remember from trig that you can spin around the circle as many times as you want, right? And you can keep getting other angle measures that are equivalent to the angle measure you found. So in a very real way, this would be the same thing as going like this all the way around here, and you'd have another theta value that would give you that same location in space. So that's one problem, right? Not problem, but it's one difference, I should say. The other difference is that the distance that we're talking about here is not necessarily positive. So you can almost think about it as, a signed difference. So right now, the way that I've drawn this r value and this theta value are positive. But you could have an r value that's negative, and it simply means you go on the negative side of the x-axis to start with. So you could take a value that you went over here first, and then you spin all the way around here, and you can still end up at that same point. So that's another way to get an additional ordered pair in polar that's equivalent to the one you had from before. Okay, so something to be aware of. There's a couple things here also that we're going to need, and that's how we go back and forth between polar, this r theta, and rectangular, x's and y's. And some of them are pretty clear as to how that might happen. If you were to think about dropping a perpendicular down like this you could measure the distance away from that axis, right? Like in an ordered pair kind of form that we're familiar with. And we would call that location or that value y. Yeah? The distance from the x-axis. And we could do the same thing and measure this distance down here. You can't hardly see it. Let me change the color so it's a little brighter. How about that? That dotted x, that red right there, that would be my x distance. So, all lo and behold, you see a lovely triangle showing up. And what's the relationship in this triangle between x and y and r?
Cosine, sine,
Okay, easier than that. Pythagorean theorem. So we're going to get some thetas here in a minute, but we know that x squared plus y squared equals r squared. That's those three specifically, right? We can also set up relationships between the angle theta and the pieces that are going on. So in particular, what if we did, you could use any of the trig functions, the ones you see them usually use as tangent of theta as our reference point first. So tangent of theta, what would the tangent of theta be for this triangle? Y over x. Now if we wanted to write it with one of the sines or the cosines, we could do the same thing too. So let's do the sine of theta. Y over r. And what you'll usually see this represented in, instead of it being written like that, is you'll see it represented as an equation for y. So y is equal to r sine theta. Okay, that's how it's usually presented. We can do the same thing with cosine. Cosine of f theta, would be x over r, right? And similarly, we could rewrite this as x is equal to r cosine theta. So moving between polar and rectangular coordinates is going to be using typically these four conversions. We don't need them all at the same time, but we just use the one we need when we need it. Okay? So we'll be coming back to those equations periodically throughout the lesson today. let's take a look at just plotting an ordered pair. So I'd like for you to do it. You guys, this is not a trig, this is a trig concept or an algebra 2 apparently concept. See if you can figure out where you would plot the ordered pair, -3, 3 pi over 2. Where would that be in space? Would it? Draw it out.
The third quadrant?
Would it?
No.
Second.
I said second. She said would it?
How about if I first tell you it's not in a quadrant at all?
It's on the line.
It's on a line.
Yeah, and it's gonna, okay.
Okay.
Oh.
It takes me longer because I'm like, how does radian work?
Okay. All right, so let's think about the -3 first. What are we going to do with the -3?
Go back.
We're going to go backwards. So we're going to go on the negative side of the x-axis, right? So we're going to start by going left 3. So this is where we sort of are beginning. I'll put a dot there even though it's not our final location. Now my angle needs to start there and it needs to go around 3 pi over 2. Where is that going to place us locationally?
0, 3.
Yeah, it is. So all the way around, like this, it's going to come up here. That's 3 pi over 2. And it would be up 3. So if we were looking at a rectangular value for where we are, it is the location 0, 3. Now, we aren't asked to do that on this particular problem. But if we were, from a visual perspective, it would be easier than the equations perspective, wouldn't it? Just because it's a nice value. So our location in space is right here. This is -3 and 3 pi over 2. Now, what's maybe a more direct name for that ordered pair in polar?
0, 3.
Nope, 0, 3 would be rectangular.
So it would be 3 pi over 2.
3 pi over 2 would be a more direct name for that. We wouldn't have to spin as far, if you will, right? Move over to the +3 on the x-axis and then spin up 90 degrees, pi over 2. Both of these are versions of the same polar coordinate. This is the one we were given. The other one is equivalent. Okay. What do you think? I don't like it. Okay, you don't have to like it. That's all right.
I don't know, that's
You'll get more. It'll be more comfortable the more you work with it. We're gonna try some more.
I
Okay.
hate circles.
I'm sorry you hate circles.
It's
Circles are nice. They're actually quite friendly. All right. What we're going to do on this one is find the rectangular coordinate for a given point. Now, I'll draw a picture when we're done just to sort of like verify that it makes sense to us. But that's not really the perspective here that's going to be most helpful anyway. But there is a correlation. However, we do have some equations that we had from slide 1. So the ones that are going to be nice are to be finding x and y. So we had equations that said x equals and y equals. What was the x equals equation?
or cosine theta.
Yes, r cosine of theta. And the y equals is
Or sine theta.
r sine of theta. Fabulous. Okay, and that's actually really nice. Number one, because we're looking for x and y. So we have equations that say x equals y equals. And we have r and theta given. So we'll be able to plug them in immediately and use them, right? Substitution. So we have 2 cosine of pi fourths. And on the other one, we have 2 sine of pi fourths. All right, so if you haven't done some trig in a while and your unit circle is not super fresh in your mind, you might want to print one out until you sort of start to piece together and remember all the pieces because we're going to be using it in the next several sections, actually. So what is cosine of pi over 4? Exactly, not with a decimal approximation you're calculating. Good, square root 2 over 2. So square root 2 over 2. So I have 2 times the square root of 2 over 2, which is what?
Square root 2.
Square root of 2. And then it's actually the same on this one, right? So we have square root 2. So the rectangular ordered pair that corresponds here is radical 2, like such. Okay, let's justify that from the perspective of a graph, just so that you can see it makes sense visually. So we're in the first quadrant, so that's the only quadrant I'll draw. It says that we go right 2, and then we go up pi over 4. So pi over 4 is halfway, right? It's a 45-degree angle. So it's going to go something like this to here. Now think about it. That location right there is on the unit circle, and it's at those pi over 2 those square root 2 over 2 values, but the radius is double what the unit circle would be at. Okay, so this one is square root 2 and square root of 2. Okay. Okay, we're going to go the other direction now. We're going to start with rectangular coordinates, 3, 4, and we're going to find the corresponding polar coordinates. So while we have an x equals and a y equals equation from the last slide, those are not the most helpful for this particular discussion. There are a couple other equations that we wrote down earlier. Those were that x squared plus y squared is equal to r squared, and that the tangent of theta is equal to y over x. Okay. The reason that those are more helpful is because the r and the theta are not in either of them together. My goal is to figure out what is r, what is theta. I can't really do that very easily if I have two equations that both have r and theta in them. It's easier if I work with equations that isolate the r or isolate the theta. Now, neither of them are actually solved for r or solved for theta. That's okay, but they still only involve one or the other. All right, so in this one, the 3 is for x and the 4 is y. So 3 squared plus 4 squared equals r squared. So 3 squared is 9, 4 squared is 16, that's square root of 25. What would you get for r?
5.
5. And to be honest,
Plus or minus.
you get a plus or a minus. Now, we'll fix the issue of which one is it. But the reality is, yes, it is. It's both, right? It can be both because we have the ability to have multiple representations for the same ordered or the same location in space in polar. So we're going to actually have answers that include both a 5 and a negative 5. On the other one, the theta. Tangent of theta is y, which is 4, over x, which is 3. All right, so we haven't done anything like this at all this semester. How do you figure out what theta is when it's embedded inside of a tangent like this? Inverse tangent, yeah. Now, if it's nice value, unit circle-wise or something like that, that's great. This one isn't. There's nothing pretty about this value, 4 over 3, in terms of a unit circle. So I can't just jump to something that I've sort of memorized along the way. I really do have to do an inverse. So we'll do the inverse tangent of 4 over 3. So grab your calculator. We'll go with 2 decimals is what I've written down. So let's go with that. If they want you to use something different, I'm sure WebAssign will tell you that. And please make sure you're in radians. We're always in radians as we're looking at this. Okay. 0.93. Okay. Here's something that you probably haven't thought of about this even up till this exact moment. This gave you one value for theta, right? But if you remember, arc trig functions, or inverse trig functions, as we're calling them right now, actually are defined on a certain interval. So you can only do inverses when functions are considered one-to-one, right? They only have an inverse when they're one-to-one. So let me draw you a picture and show you a problem. And this is not related to this question, but actually I can do that. We'll do it with tangent. I might as well use tangent here. So if I drew a tangent graph, do you guys remember what it looks like?
Yes. It's
A bunch of what?
Negative.
A bunch of asymptotes.
Negative x cubed with asymptotes.
Okay, so it looks like this if I just isolate this piece of it, right? But there's a bunch of asymptotes in reality if I continue going further out. So there's lines here and here, and it continues to repeat the process and have the same image. Okay, so everybody's remembering that, right? Is that okay? Okay, well the problem is that inverse functions means you have to switch x and y and solve for y. Well, it means you actually have to have a function, but you have to have a function in terms of y as well as in terms of x. So if I were to isolate middle, this right here, for every x value, there's exactly one y value, right? And for every y value, there's exactly one x value. But if I extend the graph and I look at both, all three pieces that I've drawn here, I don't have something that's one-to-one. What I'm saying is that for any given y value, we'll pick one, I have lots of x values, right? So the only way we can talk about inverse tangent, which is what we're talking about, inverse tangent, is if we isolate and only look at one piece of the tangent function. And the piece that we always look at is the one that's in between the two asymptotes in the very middle. That's the one we look at. Okay? So this is only giving me one value, but it should be giving me lots of values because the tangent function itself keeps repeating and keeps repeating. There's lots of theta values for which this is true. So if you think about it, the theta right here, one way to get another theta value is by adding 2 pi. Right? You spin around another 2 pi, you're going to get the same angle measure, right? So you can always do that. You can always add 2 pi. But with tangent, it's actually more than that too. It is with cosine and sine as well, but they're not quite as pretty. So tangent functions repeat their value every pi. The period over here is from, well, the period here is pi. It goes from negative pi over 2 to positive pi over 2. So every pi units, the image repeats. So the reality is over here, I don't just need to add 2 pi. I can add or subtract pi, and it will work. So 0.93 works, but 0.93 plus pi works, and 0.93 minus pi works, and plus 2 pi works, and minus 2 pi works, and it works every time for integer multiples of pi, adding and subtracting. So there's going to be some questions where they're going to ask you to find more than one representation, like here. This one says find 2 different polar representations. One of them is going to involve one of these values of r and one of these values of theta, and then the other one's going to change it. Right? We're going to change it. And we have lots of possible answers, and they're all correct. So I've got 4 of them, for example, written down on my paper. I've got 4 different options. So let's take a look at where we are in space if we're in 3-4. What quadrant are we in if we're in 3-4? We're in the first quadrant. So whatever we get for our answer, we need to make sure that we're in the right quadrant for it to make sense. Are you with me? Because I'm going to get lots of values. I can't just take 5 and join it with 0.93 pi, or 0.93 and 0.93 plus pi and 0.93 minus pi. I can't join them randomly together because some of them are going to be where I'm supposed to be and some of them are going to be in the wrong place. In particular, some of them are going to land me probably in quadrant 3 instead of in quadrant 1. So I want to make sure I'm in the right quadrant. So let's start with letting r be 5. Okay, so if r is 5, then I'm on the positive side of the x-axis, right? That's the easiest one to do. So if I have an r value that's 5, which means I'm over here somewhere to start with, how or what angle would I need to do to get up to here? And in particular, the question is, will 0.93 still place me between 0 and pi over 2? It will. Pi over 2 is about what?
90.
Well, it's 90 degrees. What is it in radians?
1.7.
1 point,
3 down to 5.
1 point, a little bit more than 1.5, right? It's 1.57-ish, okay? So if we're at 0 over here and we're at 1.57 pi, and we're at the 90 degree mark, the 0.93 is in between. So one of my polar coordinates is exactly the one that we got if we sort of maybe forgot or ignored the square root part being a plus or minus, and we forgot or we ignored the fact that we had, this multiple representations around the circle for the pi's. So one of them is the given one that seems like the natural one to find. This is the one that's the natural one. Okay? Now, we could take that 5, though, and we could take the 0.93, and we could add another 2 pi to it, right? That would just spin me circle all the way around the circle, and I'd be right back where I am. So we could add 2 pi, we could add 4 pi, we could add 6 pi, we could subtract 2 pi, we could subtract 4 pi, we could subtract 6 pi, all with the number 5 at the beginning and land right back where we are. Okay? So these are 2 options. But it's also possible to have a negative 5. So let's think about what would happen if I had negative 5. Well, if I had negative 5, I would have started out over here somewhere, and I'd have to go all the way around to get to here, right? Well, 0.93 is not going to do that. 0.93 would put me down here. How much more would I need?
Plus pi.
Plus pi. Adding pi to it would spin me the extra 180 degrees that I need to get around there. So on this one, if I did the -5, I would do 0.93 plus pi. Or I could do 0.93 minus pi, right? Or 0.93 plus 3 pi, or plus 5 pi. It's the odds, right? One of them I get the even multiples of pi, and the other one I get the odd multiples of pi. And we're just spinning round and round and round. It only asked me for 2. We've given 3. Take your favorite 2 and put them in WebAssign. You'll be good to go. Okay? But are you ready to see something cool with your calculator? You guys were pretty wowed the last time I told you to do that. Grab calculator. We are going to be in polar mode. Okay. So click mode. If you go down like 3 lines, it says function, it says parametric. We did parametric last time. Unless you've changed your calculator, it might still be in parametric. And polar, P-O-L, is the next one. Click pol and hit y equals. It no longer says y equals. What does it say? R equals. Okay, so our directions say to use a graphing utility, which we are to graph the polar equation. It says find an interval over which the graph is traced only once. So as we work with polar, the whole point is that the graphs that we're going to be working with are going to be sort of circular or cyclic anyway in nature. So go ahead and put in 2 minus 2 cosine of theta. So if you've already stepped ahead and moved too fast, you might not have a good window. So if you click on your window, for the moment, let's just let your window go from, your minimum go from 0 to 2 pi. Your theta step, you could probably just go like a 0.1. That's what we were using when we were using parametric, and that should work pretty okay for us. Our x-min and our x-max, I don't know, let's go -5 to 5, and y-min -5 to 5 for y-max. And once you've done that, I'd like for you to hit graph, and you can watch it graph something fun for you. Did you get to work?
The window.
I put my window, sorry, I don't have a way to project this. I put my window for the theta at 0 and 2 pi. And then the theta step is 0.1. And then for the x, all the x stuff and y stuff, I put -5.5, -5.5.
Confused as to like what it means to have a theta min and a theta max and an x and y min.
Okay, I can answer that. So the theta min and the theta max is, the theta is telling it how long it's going to keep drawing. Theta is talking about the drawing. It's kind of like in parametric equation when we did the t. It's telling us how it's drawing. But the graph's x-min and x-max is showing your window. It's showing where the like bounds are on the window from left to right and up to down.
Okay, so if you put like your theta max at infinity, it would just keep drawing the same
Yes, it
shape
would.
over and over.
You'd have to force your calculator to stop. But you can't really put infinity in.
Yeah.
That's not a number. But yeah, if you put something large enough, it would take it a long time to draw. Or if you're going to do like Alex over here and put like your theta step at like 0.001 or something like that, it'll do the same thing. It'll keep drawing, but really slow.
I
Yeah.
did the opposite.
You did the opposite. Okay. Did you make it look boxy?
Yeah.
Okay. All right. So did you get something that looks kind of like I don't know, it looks like some kind of a fruit to me. I'm not sure what kind of fruit it is, but I'm thinking it's a fruit. So this actually has a name. So if you look at page 725, there's a bunch of different names for these particular shapes. This one's actually called a cardioid.
Oh, of course.
Okay.
It's very natural.
And we'll sketch the graph. We haven't quite answered all the questions, but we can sketch the graph to start with. You want to take a look at where your graph is hitting the axes. So I had mine at 5, so it looked pretty clear that this is hitting over here at 4, like -4. And it looks like it's at maybe 2 and -2 on the y-axis. It might not be exactly there, but it's close to there anyway. And it's not hitting at 1. It sort of goes a little bit beyond that, and it hits back at the x-axis. So it's looking something like this. Oops, that's not right. A bell pepper. I agree with you. Mine looks even more like a bell pepper than it does on my calculator screen. It looks a little bit squished. Okay, I want you to do something for me. I want you to hit window one more time. I just want you to type in the theta min and theta max, 0 and 2 pi, just like we already did. And I want you to hit graph, but I want you to very carefully watch, okay, 0, 2 pi, and 0.1. Very carefully watch your graph and see if you can tell when it stops graphing. There's like a little thing in the top right-hand corner that shows that it's graphing and it kind of spins. And I want you to see when it stops graphing.
What do we change to?
Oh, I think you're gonna have to change. I think I have to change by R. I did it wrong. I knew I had to adjust something. Go back into R1 and just type over the equation or type over a portion of the equation. That's what it needed me to do, not change the scale. Okay. Right now, if I don't change enough, then the graph doesn't redraw. It just knows that it already drew it and it doesn't have to change anything. I'm trying to force the graph to draw itself again. I want you to see the graph graphing.
we just change the steps. Like
Change
0.1.
something. Change the
You
steps
change to
slightly.
0.09, and then go,
Sure, that'll work. Or if you change the the equals to the equation. But when you graph it and it's graphing the first time it's graphing it, right, it's got a little spinning thing in the top right-hand corner. And I want you to watch that to see when it stops graphing.
So you said
It's only graphing at once, so it's.
Okay.
we
Yeah.
change our theta max?
Theta min and theta max are still 0 and 2 pi.
Okay.
Okay. Okay, so Alex is proposing that it's probably only graphing the thing once. It doesn't look like it's repeating itself. So let's verify that with a couple of things. Take your window this time and just have it graph to pi. Just go 0 to pi and let it graph. So if we're correct, that should only graph half the graph. Did it do that? Okay. Now we want to be a little bit careful. It's not going to happen on this one, but we also want to make sure that we don't think that the graph's finished just because we did the 0 to 2 pi. When there's really more it could have been graphing, like we're going to see some loops happening and stuff like that inside of pictures later. So let's make our window go from 0 to 4 pi just to be sure that it's not sort of not graphing all of it, and do the same thing. Watch this graph, and when the image quits, the little guy in the corner doesn't quit, does he? He keeps going, but it doesn't give you any more image. The image is the same. Now, it kind of emboldens it in some areas because our T-step's a little bit off, so it's filling in some of the gaps that it didn't have. But what this is showing us is that, in fact, 0 and 2 pi are going to give us one interval. And it kind of makes sense because my equation is cosine of theta, right? So it makes sense that it would do that within 0 to 2 pi because that's the period of a cosine graph. So our interval is from 0, or at least one interval, the one we did, is from 0 to 2 pi. And we'll stop there today.